Dear students, welcome back to Signals and System online video lecture series. In this video, I am going to discuss about the introduction about the second unit, that is Fourier series. Afterwards, I am going to explain the analogy between the signals and vectors. So from the concept of signals and vectors, we will come to know that all the signals are basically vectors, so that most of the properties of vectors we can apply to the signals also. So anyway, we are going to discuss all these points in the coming classes of the second unit. The second unit is very simple and the smallest unit among all the 5 units, and we can expect the direct questions from the second unit. So second unit name is Fourier series. The Fourier series has many applications in the field of electrical engineering, signal processing, image processing, system analysis, quantum mechanics, etc. So we have the many applications from the Fourier series in various fields like electronics, like signal processing, like the image processing, system analysis, quantum mechanics, etc. So what exactly the Fourier series is? Exactly the Fourier series. A Fourier series is an infinite sum of trigonometric functions that are used to model real valued periodic functions. Here the point is very clear. Fourier series, it is an infinite sum of trigonometric functions. Trigonometric functions, we know that sine theta, cos theta, tan theta, cot theta. All these are called as trigonometric functions. Fourier series is a infinite sum of trigonometric functions that are used to model the real valued or periodic functions or periodic signals. Here the point is very clear. The Fourier series is it is an infinite sum. It is an infinite sum of, infinite means minus infinity to plus infinity. Infinite sum of trigonometric functions. What are the trigonometric functions? The trigonometric functions, we know that sine theta, cos theta, etc. Then what for this infinite sum of trigonometric functions that can be used to model, that can be used to analyze the real valued signals and the periodic signals. We have the various types of signals. To analyze or to model those signals, in which real valued signals and the periodic signals can be modeled. Periodic signals can be modeled by making use of Fourier series. Fourier series has the wide applications in a variety of fields like electrical engineering, signal processing, system analysis, and the we can have the image processing and quantum mechanics. The Fourier series having the many applications in the field of various fields. Exactly, the Fourier series is nothing but it is an infinite sum. It is an infinite sum of trigonometric functions which are used to model the real valued functions or signals or periodic signals. That means a Fourier series can be used to write a function as a trigonometric polynomial, and it is also can be used to solve the differential equations. That means what? If a system response is described by making use of the differential equations, and that can be solved by the Fourier series. Here the point is noted that in the first unit we have studied the various types of systems. Some system outputs can be described by making use of the differential equations, and those differential equation solutions can be done by the Fourier series. So need of the Fourier series. Fourier series has the many applications in various fields. Fourier series is nothing but it is an infinite sum of trigonometric functions to model the real valued or periodic signals. And that means that Fourier series can be used to write a function as a trigonometric polynomial. So that means what? We are going to use this Fourier series to write the expression for a signal. And that signal may be a real valued or periodic signals. And it is also used to solve the differential equations when the system output is described with a differential equations. This is the need and the necessity of the Fourier series. The next topic I am going to talk about in this unit, that is called signals and vectors. In the first unit we have studied about the various types of signals from its basic definitions. Now I am going to relate the signals with the vectors. What is the relation between the signals and vectors? I will explain now. As we know that signal can be represented in terms of the orthogonal function. Orthogonal function is nothing but statistically independent. From the basic definition of the signal, it is clear that signal is a function of one or more independent variable. When a function is independent, is called, it is an orthogonal function. So that signals also orthogonal function. The point is very clear. When the functions are dependent, when the functions are independent on one or more variable, when the functions are independent, then that functions are named orthogonal functions. From the signals, it is clear that every signal is every signal is a function of one or more independent variable. So that all the signals we can call as orthogonal function because statistically they are independent. The orthogonality property is verified in the vectors. In the intermediate we have studied the orthogonality in vectors, so that the signals can be represented in vector forms. So why we can treat the signals as vectors? Because if you go with the vector, definition of the vector is a quantity which has a magnitude and direction. If you apply the same definition to the signal also, signal is also having the magnitude and the direction. So that we can say that all the signals are basically vectors only. So here the point is very clear. All the signals we can call them as orthogonal functions because they are statistically independent. Signals nothing but functions are for the functions, signals nothing but the functions of one or more independent variable, that means statistically independent. So signal is also having the magnitude and direction. We can say that then all the signals are basically vectors. So we know the orthogonality in the vectors, and so that we have to apply the same orthogonality concept in the signals also. So that signals can be represented in the vectors form because we have the analogy between the signals and vectors, so that signals can be represented in vector form, so that all the signals are basically vectors. We know that vector is a quantity which has the magnitude and direction. If you go with the example, that is a running train at 70 kilometers per hour from Hyderabad to Warangal. Speed that is 70 kilometers per hour is what? It is the magnitude, and the direction is nothing but towards Warangal it is moving, so that it is the vector. If you convert that, if you say the same example in terms of signal also, signal, that means what? If you are noting down the speed of the train from 1 o'clock to 2 o'clock, and so that every instant of time we can note down the speed of the train, and it is moving towards the Warangal, and on the x-axis we can represent that distance, that direction. So that basically all the signals are vectors only. Vectors can be represented by means of arrow. We know that are directed line segment. There is a perfect analogy between the signals and vectors. All the signals are basically vectors only. We know this one. Now I am going to talk about some of the key points in the vectors. The same vector can be represented with some other coordinate system, and that is a vector can be represented as a sum of some components, and here similarly signals can be represented as sum of components. We know all these points. And coming to the some of the key points, we can understand for some of the key points we have to recall from the concept of vectors. First one is what the dot product of vector. Let u and v are the two. Let u and v are the two vectors. U and v are the two vectors. Then dot product of these two vectors, we know that dot product of these two vectors, that is u dot v is equals to, we know that modulus of u into modulus of v into cos theta. Theta is nothing but what? It is a angle between these two vectors. So here if both are orthogonal, that means what? If vector u and vector v both are orthogonal to each other, that means what? Angle between them is 90 degrees. In such cases u dot v is equals to some dot product is equals to, it is cos theta is equals to cos 90 is 0, so that u dot v dot product is equals to 0. The point is very clear here. When the two vectors are perpendicularly placed, when the angle between the two vectors is 90 degrees, then the dot product of those two vectors is equals to 0. We know this point. Other form of this dot product we can write in the form of sigma, that is sigma k is equals to 1 to n, whereas u of uk and vk, where u is one vector and k is v is another vector. The dot product, we are assuming the two vectors, that is u and v, these two are the vectors. The dot product of two vectors as given by u dot v, that u dot v is equals to modulus u into modulus v into cos theta, and when theta is nothing but it is the angle between those two vectors. If the angle is 90 degrees, that means what? Both the vectors u and v are perpendicular to each other. In such case dot product is equals to 0. This is one point. Why we have been discussing the vectors? Because vectors are signals are having the analogy is with the vector, so that once if we are good at the vectors, then we can apply the same knowledge to analyze or to study the signals. This is the distance between the two vectors. For example, I am having the vector u and v, and distance between the two vectors u and v is nothing but it is depends on the coordinate system, that is what? For example, if I assume u is coordinates, u is ab and v is cd, then we can have the distance between these two vectors, that is a minus c whole square plus b minus d whole square, under root of a minus c whole square plus b minus d whole square. This is nothing but a distance. Then the angle between the two vectors from the dot product we can write, that is what? U dot v is equals to, we have the modulus of u into modulus of v, that is cos theta. From this cos theta is equals to what we can write, that is u dot v by modulus u into modulus v. then theta is equals to what we can write. Theta is equals to cos inverse of u dot v and modulus u into modulus v. This is the theta. Angle between the two vectors, that is cos theta, is equals to, simply you can write u dot v by modulus u and modulus v. This is the dot product. Why we have been discussing this vectors? Because signals are having the analogy between the vectors with the vector, so that if you are good at these 3 points of the vectors, so that we can apply the same concepts to study the signals, that is real valued signals, and the periodic signals can be studied effectively if you know the 3 points. One is a dot product of two vectors, distance between the two vectors, angle between the two vectors, then that is simple to analyze. That is, there is then simple to analyze the Fourier series in the second unit. Then I am going to talk about the another topic now. If you are good at those 3 points, we can go for the another topic, that is called analogy between the vectors and signals. Then I am going with the analogy between the vectors and signals. Signals can be represented in the form of orthogonal functions. We know that what is the orthogonal function. If a function is independent of one, it is a function of dependent, it is a function of one or more independent variable, then that is called as orthogonal function. So that signal can be represented in terms of orthogonal function. These orthogonal functions satisfy the specific properties. Then I am going to verify the orthogonality in vectors. Orthogonal is nothing but statistically independent. So that I am going to verify the orthogonality in vectors. After studying the orthogonality in vectors, we are going to apply the same concept, orthogonality in signals. And from the orthogonality in signals, we can expect the one short answer question. So the vector said to be orthogonal if their dot product is equals to 0, then we can say that the orthogonality, if the two vectors said to be orthogonal to each other if their dot product is 0. In other words, vectors orthogonal if they are mutually perpendicular to each other. The vectors which are mutually perpendicular to each other called as orthogonal vectors. We are going with the orthogonality in vectors. Orthogonality in vectors is defined if the dot product of those two vectors is equals to 0, then we can say that the two given vectors are orthogonal to each other. Then we know the dot product of the two vectors. If the two vectors are u and v, the u dot v is equals to modulus u into modulus v into cos theta. Now I am assuming the two vectors. Are f and x. For example, I am considering two vectors, that is f and x, and so that we can have the dot product of those two vectors. I am assuming this is f, this is a vector f, I am assuming this is x. So now in that cases, then what is the dot product of this one? Dot product of this one is f dot x is equals to f dot x is equals to, we know that modulus of x into cos theta. Theta is nothing but what? It is the angle between the two. It is the angle between the two vectors. This is the theta. If these two are perpendicular, this is one vector, this is another vector. If these two are perpendicular to each other, means f will be like this. In such cases, theta is equals to what? Theta is equals to 90. So that here 90 cos 90 is 0. So that f dot x is equals to 0. That means what? if the both if two vectors are perpendicular to each other, then the dot product of those two vectors is equals to 0. This point is very clear. That is orthogonal. If the two vectors are said to be orthogonal, if they are mutually perpendicular, the vectors which are mutually perpendicular to each other called the orthogonal vectors. So this is here the theta is the angle between the two vectors f and x. Likewise, we can define the orthogonality in vectors. Now I am going to define the projection of f on the projection of f vector along the another vector x. So here I am going with one particular analysis now. So now here this is one vector, this is f, and this is another vector, this is x. These are, let assume that these are not mutually perpendicular, so that there is a angle which is less than 90 degrees, so that in such cases this vector f will project one component on the vector x. That means what? If these two are mutually perpendicular, this vector will be like this and this vector will be like this, so that no vector will have the influence over the another vector. But due to the theta is less than 90 degrees, so that this vector is going to project one component on the another vector. That component we can call as C. And this is also having the direction and the quantity, then we can call it is error vector, and it is denoted with E. Now from the from this figure we can say that Cx is nothing but Cx. Now we can call it is what? It is C, and it is a component is on x, so that we can call it is Cx. Component on x, it is nothing but it is Cx. From this figure we can say that Cx is the component of f. This is C is nothing but it is a component of f along with the x, where f and x are the two vector. In other words, Cx is the projection of f. Cx is nothing but it is the projection of f on x. Hence f can be represented as a vector addition, so that we can write f is equals to, now f is equals to, we can write f is nothing but it is one vector, and which is defining the one component along the x, so that we can write f is nothing but Cx plus E, where Cx is nothing but what? It is a component along the x, whereas E is nothing but it is the error vector. And from this we can write Cx is nothing but it is the component of, it is Cx is nothing but it is the component of f, component of f along x. That is what it is, Cx. And whereas E is nothing but what? E is the error vector. E is the error vector. Due to the sum of these two, we are getting f is equals to Cx plus E. This is one of the point is noted. That means what? We have represented the f with its components and error vector. This is about the orthogonality, one of the condition in the orthogonality. For example, if you take the this error vector is something else. For example, if I go with the another cases, that means what? I am going with the another case, that means what? Here I am defining the one more E. For example, based on the value of the angle, we can have the various values of this error vectors. Now see this one. This is error vector of the first case when this is the 90 degrees. Here this is error vector 1 and this is error vector 2. That means what? This error vector 1 and error vector 2 are greater than E, the condition, and whereas this is what? It is error vector, and in such cases we can define this one is what? F is equals to, also in such cases also we can define F is equals to, we can write here, this will define here C1 here, this will define here C2 here, so that we can write F is equals to C1x plus C1x plus E1, where error vector, this is error vector, this is 1 and it is 2. And coming to the second point, you can define F is equals to C2x, this is what? It is a C2, I can call it is C2x plus, and the error vector is E2. Likewise, we can define these points, so that here E is, here in these three cases, wherever E is minimum, then only we can say that F is perpendicular to X. Where we can get this E is minimum, that means what? If we are having the F and X are with the theta is equals to less than 90 degrees, it is projecting one component here. If this theta is 90 degrees, this F will go like this and X will go like this, so that F will not define any component, or F will not project any component on X, so that there is no E, there is no error component, such that the dot product of those two vectors will be equals to 0. That means what? At theta is equals to 0, at theta is equals to 90 degrees, E is equals to 0. If theta is less than 90 degrees, if the theta is less than 90 degrees, E is not equals to 0. So whenever the two vectors are mutually perpendicular, we can say that the angle between them is equals to 90 degrees, then the error signal defined by the one particular vector is going to be 0. And this is what? E is nothing but it is error vector. Error vector can be existed whenever theta is less than 90 degrees. Here theta is, we are saying it is less than 90 degrees, so that it is defined error vector here, and by changing the theta again it is not equals to 90 degrees, and again it is defined one more error vector, that is E1, and so that it is defined one component on along the X, that is C1, and if by changing the theta again, and we have the another error vector, that is E2, and it is defined the one more component on C2. If the theta is exactly 90 degrees, this F will not project any component on X, because F is going like this and X is going like this, so that there is no projection of F along with the X, so that there is no component will be defined and there is no error vector, so that whenever the two vectors are mutually perpendicular to each other, then the angle between them is 90 degrees. The dot product of those two vectors is equals to 0, then the error vector is also 0. This point we have to apply. These points we have to apply to the signals also. Now we are discussing orthogonality in vectors, but we have to apply the same knowledge to the analysis of the orthogonality in signals. Then I am going the one more concept now here. For example, here the component of F along X, or projection of F on X is Cx. So it is also given as we can have this is, from this equation we can write that C into modulus of X, this is nothing but it is what? It is a component along with the X, component along X, that is Cx is equals to, we can write this one is modulus of F into cos theta. If you wanted to convert that is into the dot product, we have to multiply with the X. Now I am going with the multiplying with the X. See this one, this is C into modulus of X into modulus of x is equals to, we can write modulus of f into modulus of x into cos theta. This is nothing but what? It is a dot product of, it is a dot product of the two vectors, that is f and x. We can write this is nothing but dot product of two vectors f and x is what we have now, c into modulus of x square now. And from this what we can write, c is equals to, from this what we can write, c is equals to, we can write f vector dot product of f and x by x square. X square I can write this is about x modulus of x into modulus of x. So that this, in the above equation, x will not be cancelled, since f dot x is a dot product and x dot x are, x and x are the vector products. So that this is the condition for the orthogonality of vectors. Now I am going to explain if the angle between these two vectors is equals to 90 degrees. We have the formula is what? F dot x, that is a dot product of two vectors. F dot x is equals to modulus of f into modulus of x into cos theta. Then now I am saying that these two signals are orthogonal to each other. If these two signals are orthogonal to each other, what happens? This is f, assume that this is f and this is x. Now it is x, it is a vector, and this is f, this is another vector, and so that the angle between them we are assuming, it is a 90 degrees now. 90 degrees means what? It is a vector which is having the magnitude and the direction, it is moving like this, and it is also one more vector, it is having the magnitude and the direction, so that it is also moving like that. So that in such cases this f will not project any component on this one. That means what? The component here c is equals to 0. Projection of component, the projection of f along x is 0. That means c is equals to 0 now. C is equals to 0 due to the angle between them is equals to 90 degrees. So that in such cases what we can write, f dot x is equals to, and modulus of f into modulus of x cos theta, theta is equals to 90 degrees, cos 90 will be 0, so that we can write f dot x is equals to 0. The point is very, very clear. When the two vectors are orthogonal means angle between them is 90 degrees, so that no vector will define the component on the another vector, or we can say that no projection of one vector along another, so that there is no component is defined along with the another vector, so that c is equals to 0 if the two vectors are perpendicular to each other. So that points here we have to define. First one is when the two vectors are orthogonal to each other, theta is equals to 90 degrees. When the two vectors are orthogonal to each other, then the theta is equals to 90 degrees. Then the dot product of those two vectors is equals to 0. Dot product of two vectors is equals to 0. In that cases there is no projection of one vector along another, so that the component c is equals to 0. If the component c is equals to 0, then the error vector is also 0. These are the 4 points to be noted in the orthogonality of vectors. First point is what? First point, when the two vectors are said to be orthogonal, then the angle between them must be 90 degrees. Then the dot product of those two vectors must be 0, because cos 90 is 0. 0 into anything will be 0. And so that if two vectors are orthogonal, one is going exactly perpendicular to the another vector, so that one vector will not project any component along the another one, so that that will not define any component, so that c is equals to 0. If c is equals to 0, there is no scope of error vector, because see this one, If the angle is less than 90 degrees, then only there is a projection, then only it is defining the component C along X, then only we will be having the error vector. But if it is having the 90 degrees, that means what? Here the 90 degrees, it is going like this, it is going like this, so that there is no projection of F along X, so that there is no C. C is equals to 0. If C is equals to 0, then the error vector is also 0. Likewise, we can go with the orthogonality in vectors. Same 4 points we have to apply to the orthogonality in signals. Why we have studied orthogonality in vectors? Because signals are having the analogy with the vectors. Basically all the signals are vectors only. So that to understand the signals, first we have revised the vector properties such as dot product and angle between those two vectors, distance between two vectors we have studied, and after that we have to apply the same concepts to study the signals. Because signals are nothing but signals are basically those are vectors only. The 4 points we have to apply to the signals also, and such that we are going to study the orthogonality in signal. 4 points are very, very important. Orthogonality is nothing but what? The angle between the two vectors is 90 degrees, then we can say that the signals are orthogonal to each other. If the angle between them is 90 degrees, then the dot product of those two vectors is equals to 0. So that third point, no vector will project the one component on another. That means what? Component C is equals to 0. Then there is no error vector. And if you are good at these 4 points, we can apply the same concepts to the signals also. Thank you, students. In the next class, I am going to explain the orthogonality in signals. Orthogonality in signals. In this class, in entire class, what are the key points you have to note? First key point, F is equals to Cx plus E. And this F is a vector, X is a vector, where C is a component and E is a error vector. If we apply the same concept to the signals, F is a signal, X is also a signal, C is a component. Here E is a error signal, not error vector. It is a error signal. This is the first point. And here, if the two vectors are orthogonal, then angle must be 90 degrees. So in the same case of signals also, if the two signals are orthogonal to each other, angle must be 90 degrees. Then if two signals are orthogonal, the C will be 0, this will be 0, and the error signal is also 0. These points has to be applied to the orthogonality in signals. In the next class, I am going to explain the orthogonality in signal. From the orthogonality in signal, we can expect the one short answer question or one long answer question for the 5 marks. So that it is very, very important. So don't miss the class. And I seriously observed that most of the students are not watching the complete videos. They are not at all giving the attendance in the comment box. It is strictly violating the rules of attendance precautions. So students, watch the complete videos and try to understand the subject, and try to give the try to write the notes from your shared videos, and give your attendance through the comment box after watching the videos. Thank you, students. Thank you so much.